We lost half of the audience. Okay. So how do I make it so we are halfway through the course. Let's see if I manage to keep the remaining half of the audience. Okay, yesterday we stopped. Let's put it. We stopped here. By the way, here you find the notes. So this is my home page, and then you go and click on the teaching. There are a few sub-pages. You go to the sub-page teaching, and then you find the link to the notes. The notes are comprehensive. Okay, you remember yesterday. Yes, the same notes I sent you to Susanna, yes. Okay, so we are looking, gravity is responsible for both things, no? Attraction between bodies, no? Newtonian potential, general relativistic radiation, and radiation. So now we focus on radiation. We look at the transfer traceless component of the metric perturbation. And so to do that, we have to solve the box equation with the retarded boundary condition. Okay, divided by x minus x prime. Here there is minus 1 over 4 pi, which is the normalization of the Green function. And then there is a 16 pi g, which is from the Einstein equation. There was a minus 1/2 here, then here become plus because it's minus 1/4 from the Green function. There was a minus 1/2, and there was 8 pi g from the Einstein equation, and we get this. So you can do the simplification. Here you get 4. So we stopped here, and actually I said, look at this. And then crucially, there is a lambda tensor here. So this is the energy momentum tensor, which is on the right-hand side. And then there is the lambda tensor that projects only to the radiative degrees of freedom. No, you remember. So HP nu has 10 components. 4 are pure gauge, 4 are longitudinal, they mediate potentials, and 2 are radiative. You remember in the first lecture we saw that the longitudinal mode satisfies a Poisson equation. And then the radiative mode satisfies a box equation. This makes a whole lot of difference, no? Because in the box equation you can have the source, and so you find the specific solution, the peculiar solution, and then you find the homogeneous solution. This equation is an homogeneous solution which is not vanishing. Okay? So this equation you get, for instance, a plane wave, whatever depends on t minus z or t minus r, it's a wave. In this equation you don't have homogeneous solution. No? The homogeneous solution is 0. You just have a solution if you have a source. If you don't have a source, this is 0. So this is the reason why not only we kill 4 degrees of freedom when we go and look at the radiative, but we kill the 4 longitudinal degrees of freedom, because when we look outside the source, we kill also the longitudinal degrees of freedom, and we can focus only on the radiative one. Now that we have only the radiative one, yes. Sorry? So the question is about the integral. D3x is okay now? It was missing D3x prime. Of course, I integrate over the source, and the Hij, the field, depends on t and x. Okay? So I look at the field far away, and then I integrate over the source, actually convolve the source with the Green function. That's standard thing, no? In electromagnetism too. And then you remember we look at the observer, and then the source is somewhere here, and then we have this huge distance, d, and then we have, well, we always call it r. Let's call it r. You have this huge distance, and then we have x prime that runs over all the points of the source. And then, you know, there is the Pythagoras theorem that this argument here, x minus x prime, we expand it, and we say that x minus x prime, the modulus, is equal to r minus plus order of x prime square over r. And so it's completely negligible. Okay, now this is clear. I'm just doing the, these are two vectors. The modulus of this will be the square root of r square plus the modulus of x prime square, which is the vector running over the source, minus 2, the scalar product of x r prime. Then I expand the square root and I get this, and I get some subleading order which I can kill. So in the denominator, I don't care about keeping the dependence on x prime. In the denominator, I just say that this is r. Here, I don't care. In the numerator, yes, I need to take into account the effect of the retardation, because this is order 0, this is t minus r. This minus r is just the offset, it's just the retarded time in which I'm looking at the source. But then each point of the source, I'm looking at it at a slightly different time, depending on if it's closer to the observer or if it's farther. And so I have to expand. In this guy here is very little compared to that. This is clear, no? Because this is the side of the source and this is the distance. So let's expand the integrand. So let's forget the projector now. Let's expand the integrand. And so you get TKL. So order 0, I get this. So 1 over r, I can put it outside of the integral because I forget the x prime dependence in the denominator. And then I expand first order, I get T dot. Okay, there is a dot here. I cannot make the dot. A big dot, yes. T minus r, and then I get the delta x over expand. And then there is the second order. 2 big dots divided by 2, t minus r, and then there is n times x prime square. And then, of course, all possible orders you can imagine they appear there, okay? So it's clear, no? Dimensions are safe because this is t with one derivative, but then I multiply by one length. This is t with two derivatives, but then I have two lengths, so dimensions are safe. But then, if the expansion makes sense, this term must be smaller than that, and this term must be smaller than that. So what is the expansion parameter that allows me to go to one order to the next one? Have you thought about it? Yesterday I stopped here. So these 10 minutes were just the recap. You remember, so look at this. This is the energy momentum tensor of the source. The source, the prototypical source for us is a binary system. So when I take a derivative with respect to time, this corresponds basically so a dot, a big dot, is the same as 1 over the period of the source, okay, as a scaling. Are you okay with that? I don't see nodding faces. I assume you are nodding in your hearts. So, and x prime is just the size of the source. So the x prime, you see, the x prime and the dot are what are extra in this order with respect to the leading order. And this corresponds to L over T, the size of the source divided by the typical period of the motion of the source. And this is equal to the velocity, the internal velocity. Very good. Okay, so the small parameter that makes me go from this to this is V. And clearly, it's the same here and the same over there. Okay, so this expansion that I do for small size of the source in the argument of the energy momentum tensor for the retarded time is actually the velocity. So this order is V suppressed with respect to that, this order is V suppressed with respect to that, and of course I have infinite orders. And this also tells me that when my source has some internal velocity which is close to the speed of light, then this expansion is not very suitable. Okay? This is only suitable as long as the velocity is 20% the speed of light, 10% the speed of light, okay? No more than that. And now there is another trick that we have to apply, another very standard trick, which is the following. We have to take the integral, now that we have expanded, so order 0 is this. Order 0 is this, okay? This is the order 0, we have to take the integral. You remember there was a dependence on x prime also in the denominator, but that I forget. I said that x prime, the size of the source, kilometer, is completely negligible with respect to the 100 omega parsec. So I take it out, it doesn't belong to the integral. So the integral is just, I have to integrate the source, the energy momentum tensor. Now there is a standard trick. I want to trade this object for moments of the mass. Okay, this, if you have never seen it before, you say, where the heck does it come from? Well, think of the scaling of this object. These are the space-space component of the energy momentum tensor. The space-space component of the energy momentum tensor, how do they scale? So, the energy momentum tensor say T00 is rho. If I would have T0i, I would expect a momentum, a density of momentum. So T0i will scale at rho v. Tij or Tkl, I expect it to scale as rho v square. Think of the energy momentum of a point particle. It scales like this. And then once I integrate, this scales like mv square, the kinetic energy of the system. But the kinetic energy of the system is something that, you know, if you really want to monitor it, you should know too many details of the source. What we want to say that this object, we want to trade it for some moments of the energy momentum of the mass. Clearly, this object, it cannot be the integral of the mass, no? Because the integral of the mass density. The integral of the mass density is the mass, which is not the kinetic energy. But, and also this object has two indices, this object has no indices. So if I put here an xk and xl, this is the second moment of the mass density. So once I integrate, this by definition is the quadruple, no? This is the definition. The second moment of the mass is the quadruple. And so this has two indices like that, but it's still not a kinetic energy because it's mass times two lengths. This is mass times two velocity. But then if I introduce two derivatives, you see, this has the same scaling. This is mass times velocity square. This should be, of course, this heuristic argument doesn't guarantee that the coefficient, that the two are equal exactly, but there could be a numerical coefficient. But you know, heuristically, we say, these have the same rotation transformation. Two indices. Have the same scaling with the velocity, because this is mass times x dot times x dot. So the scaling is the same, the rotational transformation is the same. Maybe the two objects are the same, modulo a factor. Indeed, it is so, and let's derive it mathematically. Yes. Yes, I mean, if I say the mass of the energy momentum tensor is a density, okay? So it would scale as mass divided by volume, no? Energy density. Sorry, I have to repeat the question for people in Zoom land. So I was asked to repeat the argument of the scaling. What do I mean with scaling? So energy it's a little bit more than dimensional analysis. So you have to think of dimensional analysis and make it a bit smarter. Just a bit smarter. It's basically dimensional analysis. So energy momentum tensor, all components have the same dimensions, okay? So the dimension of mass divided by volume, no? It's an energy density. But what I'm saying now is that each of the components has slightly different scaling, in the sense that T00 doesn't scale with velocity, no? It doesn't matter, I mean, as long as the system is non-relativistic, and I put some energy density, no matter what is the velocity, the total energy is the rest mass, as long as the velocity is small. So the integral of T00, the integral of T00 is always the mass. The integral of T0i as dimension is the mass, but as scaling not. I mean, because T0i is a momentum density. When I integrate, I obtain a momentum. So this must scale as mv. So if the object has no internal velocity, is static, the integral of T0i is 0. Which, by the way, 0 is also dimension of a mass, as 0 can have any dimension because it's 0. So dimensionally is correct, but well, I want to know something more. So the integral of Tij or Tkl would be something like mv square, because just look at the energy momentum tensor of a point particle would be something like mass vi vj. Rho Vig, once I integrate, will be order of mass v square as a scaling. The dimension of all of these are energies, but they scale slightly differently. So what I want to make the point here is that the integral of TKL, which scales as mv square, is the same as the second derivative of the second moment of t0, 0. Okay? So there is a mathematical trick to derive it. The mathematical trick is not very illuminating. It's just a way to get the coefficient right. But before I do the mathematical, because if I just do the mathematical trick and I write down the equality, you might say, well, where does it come from? And then tomorrow you try to derive. The mathematical trick is a bit tricky. It's a trick. You won't do it right again. But if you know the result to guess, then you have more chances to do it right. Trust me, because whenever I teach this for the last 5 years, and every time I have to look the trick because I forget it. But since I know the result, then I managed to find my way to the result. Okay? So, energy density integrated scale as mass. Momentum density once integrated scale as mass v. Stress, remember the space-space component of the energy momentum are the stresses. Once integrated, it scales mv square, where this v, of course, has nothing to do with the global velocity of the source, no? It has only to do with the internal velocity of the source, no? Because the global velocity of the source, we don't care really. We go to the reference system in which the source is at rest, and then if you want to go to a system where the source is moving globally, we just make a Lorentz transform, a boost, or a Galilean transformation. Okay. Shall I? Other questions on this? Okay. So I move on to demonstrate this funny relationship, and I do it in steps. Let's see if I can do it right. So the trick is the following. I say that integral of Tj, I want to trade it for some 0k. Yes, you see that the trick is this. Let me check. Yes, now I remember. Kij plus t with some coefficient. I want to trace it with this, Tkj xi. This is the standard trick that allows you to trade the moments of the space-space component of the energy momentum tensor for moments of the mass of the source. I hope you can read what I wrote. And, well, it's actually not correct. The correct thing is this. So I will write repeatedly variation of this identity. I will write many times. I will repeat many times. So this is at the end of the day, I want to have a Tij without moments. And you see, this is one moment of Tij, but then I take a gradient. So heuristically, we are there. But we know that this is 0, okay? Because the source is confined to a tiny region of space, and this is a total divergence. So a total divergence of something confined in a finite region of space, it can be traded for an integral of a surface at infinity, but the source at infinity is 0, so this must be 0, okay? So this is a general statement. The divergence of something confined in a point or in a small region of space, once you integrate, is 0. Once you integrate, of course, this locally is not 0, but once you integrate, is 0. So let's do the integration by hitting with the gradient once here and once there. So if we hit once here, we get Tki xj, comma k, plus Tkj xi, comma k, and this must be equal to minus T ki delta jk minus Tkj delta ik. So now I'm just lazy, so I don't write the integral sign anymore, but whatever I write from now on, it's only true under the integral sign. No? This is not valid locally. It's only valid once I integrate, because I use the fact that the integral of the divergence of an object which is confined in a tiny space is 0. So let's go on. I use first the divergence theorem, and then second ingredient I have to use conservation of energy momentum tensor. Conservation of energy momentum tensor tells me that this is minus T0I dot xj, no? Because T0I dot plus Tkk dot ki gradient must be 0, so this is minus, and this is minus T0j dot xi, big dot here too, is equal to minus tij, minus tij, I put a 2, and then I change all the signs to plus. Okay, mathematically, I mean, I did trivial things, mathematically. But physically, there are a lot of things going on here. You see, I'm trading the integral. Again, I always understood the integral sign. I'm just lazy to copy it all the time. I trade the integral of energy momentum tensor for first moment of the linear momentum part. Okay? And of course, a derivative has appeared just to save dimensions, okay? Because if I put one moment, I increase the length by 1, then I have to decrease the length by putting a derivative. So now let's go on. So this is not quite what we wanted. We wanted the Tij, I mean, this is correct, but it's not what we want. I'm trading Tij for first moment of momentum density, the first derivative of momentum density. So what I want is to take this. Let's forget the derivative, we'll add later. I want to trade this for a second moment of T00. How do I do it? Well, now you know the trick. Yeah, do you? Have you learned the trick now? So I say that TKL xi xj, comma KL has to be equal to 0. Or let's derive only once. Okay? You see, I want to trade this object, which is the first moment of a linear momentum, for a second moment of a T00. And I can do with this trick, because look at here now. This is 0, again for the divergence. Then I apply the divergence once here and once there, and then I get minus T0k, comma k, xi, xj, so I applied here, I brought it to the other side, equal to T0k delta I k xj plus T0k xi delta jk. Okay? So this is equal to plus T00 dot xi xj, and this is equal to twice T00, not T00, this is equal, not twice, is equal to T0i xj plus T0j xi. Okay? It's always the same trick. I mean, you increase the moment by 1 and you add a divergence that you eventually contract with one index of the energy momentum tensor, and so you trade a higher moment of an energy momentum tensor component with more 0 in the indices with the integral of an energy momentum tensor component with more x's. And you see, we obtain this. We can add a derivative. And so look at what have we found. We have found that this object that was this, it stays. This object is the same as this. On one side is equal to twice Tij, on the other side is equal to the second derivative of xij. So we have done what we wanted. We have related, now I put back the integral, just to state the final result. I obtained that TKL is equal to 1/2 the quadruple second derivative of KL. Okay? And so in the formula for gravitational wave perturbation, I will never talk about integral of the space-space component of the energy momentum tensor, but I will always talk about second derivative of the quadruple. I mean, as you see, this is something that we have expected. Here there are two indices, then we must have a second moment. Then we must have two derivatives to compensate the dimension, and the 1/2, okay, the 1/2 you cannot guess. You have to do the computation to get it right. Okay, so we go back to the result, and we find that Hij is equal, there was a 4, so now it becomes a 2, because there is 2g divided by the distance to the source to the observer, q double dot kl, and then there is the projector, lambda ij kl. This is important, no? Because there is the projector, because otherwise we don't get, otherwise we are polluting the perturbation with some objects that are not the radiative part of the field, that are the longitudinal part of the field. For instance, if you want to go back, let's see how this is derived from a Lagrangian formalism. In a Lagrangian formalism, you should write, instead of the equation of motion that are Einstein g mu nu equal to 8 pi g t mu nu. In the Lagrangian formula, we should have 1 over 16 pi g integral of d4x square root of minus gr plus Lagrangian of matter. And then we know that the energy momentum tensor is defined as twice minus square root of g ds in the variation. Is everybody fine with this? I mean, I just the usual definition of the energy momentum tensor is the variation of the matter action with respect to the metric tensor. Okay, if you look at it in how the Einstein equations are derived in a Lagrangian formalism, we perceive something interesting. And about this, there is an exercise that I already precise. So pay attention now. What you have to expand the Ricci to quadratic order. And so the expansion is a bit ugly, but it's not ultra ugly. But as you can imagine, I don't remember by heart. As far as I know, nobody remembers it by heart. But you have, okay, this is the structure of the expansion of the Ricci to quadratic order. So we need quadratic order to get linear equation. No? That's why people usually work directly at the level of the equation of motion, because then everything is linear. But if you want to work a linear level in the equation of motion, you must be quadratic in the Lagrangian. So for electromagnetism, it's not too hard, f squared. For gravity, I mean, it's not too complicated after all. So you must have the quadratic expansion of this. I mean, what structure you can have? You can have this structure, then you can have the extraction with appropriate coefficients, which is minus, if it's minus 1/4 here, then here is minus, and then you have two more structures. Yes, which are d rho h rho nu d mu h mu nu with the minus 2. And then you have one final structure. This is not the most generic structure, but is a structure that has very nice properties. Okay, so this is the structure of the quadratic term of the Ricci. And then let's look at the coupling to matter. The coupling to matter, by definition, appears to be something like this. It's 1/2 t mu nu. Let's put the indices aside. So as you can see, I'm a cavalier with the space indices. I move up and down without any problem because I use mostly plus metric. So I have to be careful when I move up and down time indices. So remember, according to the scaling we used before, now we have to be careful when we expand if the index is time or space. Okay, so this will be something like 1/2 t00 h00 plus h0i t0i plus 1/2 hij tij. Okay? At the end of the day, you remember, when we solved the level of the equation of motion, we got a box that clearly comes out of the inversion of the kinetic term. No? This is all the complicated, it's not too complicated, it's a big complicated kinetic term of h. So when you derive the Lagrangian equation of motion, you get a box h. Truly, you don't really get a box h, no? You get something more complicated because this kinetic term is not invertible. You have to fix the gauge. And you fix the gauge adding an appropriate gauge fixing term. But the important point is that there is a linear coupling here. And so the Euler-Lagrange equation on the F2 pieces, dl in the h, you first derivate with respect to derivative of h, and then you take another derivative. and then you derivate with respect to the underivated h, and then you get the coupling to the source. You see, in principle, the source couples to all of h, no? Couples to hij, couples to h0i, and couples to h00. But when we look at the waves, where have they disappeared, these two couplings? I mean, we kill by hand, no? We kill by hand with the TT condition, because we use the gauge transformation that kill these pieces. But these pieces are not zero, they are just not radiative. For instance, in Schwarzschild, H00 is 2 GM over R, you know? No? This is the Newtonian potential generated by the source. This T0i, well, if the object has no angular momentum, this T0i is proportional to the displacement velocity of the object. If the object has an angular momentum, this object is proportional to the angular momentum, okay? But again, this is not radiating, no? It's generating a static field like in the Kerr solution, but it's not generating a wave. That's why when we kill by hand those components, then we obtain a solution that starts with this piece. This piece is the part of the energy momentum tensor that is starting to source radiation. And then we traded for a second derivative of the second moment of the mass, also known as quadrupole. Okay? So let's pause just a second to... So this is the Lagrangian term. Once I integrate it, this should appear as... If I think of my object as living on a word line, then I have an action which is just the integral over time of the word line. And then the first coupling will be the integral over d3x prime of t00, it's just the mass coupling to h00. And then I have the second piece, which is the coupling of, so this comes with an half because of the definition, and this is h0i plus hi0, so it comes without the half. And then we get, if you like, t0i, integral of t0i. There is the integral over dt and the integral over d3x prime. Okay, you see, these are the two non-radiative couplings. This is non-radiative, this is non-radiative, this is the radiative couplings. But remember, we have to do the expansion over retarded time on these two. Yes, yes, thanks. Okay, so what happens here? My coupling, you see, this is the source, and this is the field. The field which is generated by the source has a long variation. So what I want to do is to Taylor expand, like I did for the solution of the tensor structure. Now I want to do at the Lagrangian level. I expand this as T00, and I take the integral only over him, because H00 now it's Taylor expanded. And then I take T00, first moment, and then I integrate by H00, I. And then I take T0i, and I do this. Actually, here I will need also the following term. T00 xi xj, 1/2 hij, sorry, H00 comma ij. And then I take a T0i and I expanded T0i d3x, this is H0i, T0i d3x plus T0i xj, H0i comma j, and I integrate in d3x only this. Okay. Say it again. So, yes, I realized that it's not very easy. This line was confusing for you? Which? This line was confusing? So, this is gradient, sorry. It's not, I understand, it's not easy to read, but A00 I J. Okay? So now I'm taking a step. I focused so far only on the radiative degrees of freedom, no? Until 5 minutes ago, no? We were only dealing with the radiative degrees of freedom, and we were working at the level of the equation of motion. At the level of the equation of motion, I had to invert box H equal to Tij. I inverted, and then I traded Tij for a second moment of the second moment of the mass density. Now I want to show you something more. I want to show you, that you have to, when you work at the Lagrangian level, you have to do this Taylor expansion. I mean, doing that work of expanding the source. It means that the source has a scale variation just on a tiny space, whereas the field that you're looking at far away, scale, okay, now I use R for the two things. The field that you're looking for far away of the source, scale is 1 over d. It has a long variation, whereas the energy momentum tensor, it has a variation of a much shorter scale. It has a variation in scale as the size of the system. So what happens here, look at the scaling of these two objects. You see, when I do this Taylor expansion, I'm implicitly assuming, for this expansion to make sense, that there is a variation of the gradient of the field, and there is the variation of the source. So the source has a size L, whereas the variation of the gradient of the field, well, for this field, which is associated to a conservative field, this is just the Newtonian potential, the variation is the big distance. For Hij, which is the radiative field, the variation is lambda. Hij has a variation which is 1 over lambda. Okay? Because yes, its goes is 1 over d, but 1 over d is the distance source observer. So while H00, it has a constant divided by d, so if you take a gradient, you will divide by d. When you do Hij, you have to be, the numerator here is not a constant. The Hij depends on the kinetic energy of the source. The kinetic energy of the source is varying, no? The kinetic energy is not conserved. The total energy is conserved, the kinetic energy is not conserved. And so what you get here is that the Hij as a the Hij, the gradient is basically Hij divided by lambda, okay? So the radiative field has a variation that depends on the lambda, that is the wavelength. And the wavelength, how it is related to the scale of my source. My source has a scale little r and has a period of t, okay? What is the lambda? The wavelength of the radiative field. Think about it while I take off my pullover because it's getting hot here. It's the first time I work since I got to Buenos Aires. Yeah, you said? No, the velocity, lambda is equal to r over v. I mean, it's clear, no? Lambda is related to the wavelength of the system. This is a wave, this is a real wave, so the period of the wave is equal to lambda. And the period is r divided by v. So v is, sorry. Okay. Yes. Okay. Clearly, v is 2 pi r over t. Okay, we forget about 2 pi's here. We just worried about the scaling. So the lambda is equal to t is the same thing as r over v. So the radiative field has a variation that scales over lambda. The non-radiative field has a scale that is even longer than lambda. So it makes sense having this Taylor expansion even at the level of the Lagrangian. You integrate, I mean, this is slow varying field. So in principle, this should be under the same integral sign. You should integrate over all of the space. But this is the slow varying field. This is very slow varying field. This is very slow varying field. This is very slow varying field because these are the conserved field, no? The field that are sourced by conserved current, by conserved mass, conserved momentum, conserved angular momentum. And then you have Hij, which is varying on a time scale, which is which has a wavelength and is varying on a time scale, which is R over V, which anyway is much longer than R. R over V is much longer than R. Whereas you see these T00, T0I are non-zero only on the size of the source, which is R. Okay? So it makes sense to integrate this and to Taylor expand the rest outside. So when we put all of these together, look at what we obtain. We obtain this coupling, then we obtain T00 xi h00, I plus T0I h0I. And then I obtain Tij Hij plus 1/2 plus 1/4 T00 xi xj h00 ij plus T0I xj h0 ij. Okay? I'm expanding the coupling T mu H mu. I'm breaking the covariance. I'm breaking space and time. So I get coupling to conserved source, coupling to the dipole. This is T00 xi. This is the dipole, and here I have one derivative. This derivative is the derivative that gives me the gradient of the emitted field. If you like, it could be the frequency of the system. And so these two pieces, I can put them together. And using the same trick as before, I can show you that. Just a second. Yes. I do the same trick as before, and then I show you that T0I is equal to, always under the integral sign, T0K x I. Well, we do this first. Okay, so this is 0. It's always the same trick as before. Now this is a total divergence. But then now it becomes a non-trivial 0 because I separate the two pieces. So on one side it is minus T0K gradient K xi, and on the other side is T0I, no? Because this is delta Ik and gives me T0I. Then I use the usual trick of a conservation of energy momentum tensor. So this is T00 xi dot, which is equal to T0I. And so you see, these two objects, they deserve to be together, okay? These two objects, this T00 xi and T0I, they deserve to be together. Of course, they don't have the same dimension, but here there is a derivative. So if I use that T0I, I trade it for T00 dot xi, look at here what happens. Here it happens that I get a coupling of T00 xi. Oops, I forget. I get T00 xi, okay, with the 1/2. To H00I, and here I trade this T0I xj. No, sorry, I was trading this. I traded T0I. I traded for a. it's here. I trade it for a t dot. Okay, I trade it for a t dot. No, it's this format, t dot t00 xi. And I couple it to t0, it was here, t0i, a0i. And look at this. Now I do integration by part. All of this is at the level of the Lagrangian. In the Lagrangian, I can always do integration by part. So here, okay, this was the ti. I put a minus. I cancel this. And I put the dot here. No? I move the dot from here to there, and I put a minus. So now I have t00 xi that I can put in evidence. And I get and here I get 1/2 t00 xi. Okay, so you recognize what is this? This is the linearization of gamma I00. Okay, so my Taylor expansion at the level of the Lagrangian is I find it a bit more illuminating. You might disagree at this moment, but believe me, it's more illuminating. Is that at the end of the day, when I do my Taylor expansion at the level of the Lagrangian and not the level of the equation of motion, I obtain mass coupling to H00. I obtain first moment of T00. What is the nickname of the first moment of T00? T0, the integral of T00 is the mass, no? If I take the first moment of the mass, this is, say the dipole, okay? Yes. So, after the integration, I get the dipole here, the couple to the linearization of this Christoffel. And then, you see, here I have mass times H00. Here I have mass times length times a derivative of the metric. Okay? And then in the following order, I get here. I get the Tij, Hij, which are already traded for Qij double dot for Hij. There was 1/2 Tij, Hij that I traded with this. Then I got to the 1/4 H00 Ij T00 Xi Xj integrated, but okay, wait. The second moment of T00 is the quadruple, so let's write the quadruple. And then I had the other piece, no, the first order expansion on Tij. Which I write like this. So I see blank faces. Did I lose you? I'm doing something that, I mean, it's kind of straightforward. I take the coupling at the level of the Lagrangian. Okay, this is the fundamental coupling. By definition, the energy momentum tensor. Let me recap because I don't see people following me. So this is the T mu coupling linearly to H mu. This is the definition. T mu is what by definition coupled linear to H mu. Then I do two things. First thing, I split mu to 0, 0, 0i, and ij. Why? Because in the back of my mind, I'm always thinking about non-relativistic sources. So T00 scales with V to the 0, T0i scales with V to the 1, and Tij scales with V to the 2. So I want to separate powers of these. Okay? So this is the first thing that I do. And then the second thing, and to apply the standard trick. The standard trick is to trade moments of space part of the energy momentum tensor, sorry, space integral of space component of the energy momentum tensor for moments of the mass, for moments of the energy density. So these are the two tricks. When I do these two tricks, then I obtain, the passage is I obtain the standard coupling of Hij to the second derivative of the quadrupole. This is the truly radiative coupling. I obtain this coupling, the second moment of T00 coupling to the gradient, second gradient of H00, just the Taylor expansion. And then you see the first order Taylor expansion of H0i, I split into two pieces. One piece in which A0ij, H0ji is symmetric, and one piece in which is antisymmetric. Sorry, here I was missing an index. And here there is Hj. Okay? Of course, this is the first moment of T0i that couples to the first gradient of H0i. Okay? And then I split into these two pieces. This is mathematically trivial because you see this piece cancel that, and then I add the two, I obtain 1/2 T0i xj. I just do this because this piece, now I collect all of them together. And using the same trick as before, this will be, you remember, this will be first derivative, first time derivative of second moment of T00. Same trick as before. You see there are two indices, so it will be traded for second moment of T00 with one time derivative. And so all of these are the same order. This is also the same order, but look at this. So let me separate this. Remember, two tricks. Separate space and time, and then do Taylor expansion. Separate space and time, do Taylor expansion. Then I get the 1/4 Qij, Hij. Let me integrate by part twice and put the two derivatives here. Then I get the 1/4 Qij, H00, comma Ij. And then when I use the standard trick of trading first moment for second moment of T00, from this I obtain H0i, comma j plus H0j, comma I obtain with the Q dot, because the standard trick it was in the page before. You can check in the page before that. In the page before, you will see the trick. It's here. You see? First moment of T0i, symmetrized, is second moment of T00 with two derivatives. So I just plug it back, and I get this. And I get one derivative, because one gradient, and then I integrate by parts, and I move this dot here, I move it, it's a mess. And I move it, sorry, this is a Q, Ij, I put a minus because there was one time derivative that I move by part, and this will be minus 1/4 H dot, H dot. Okay, so look at this. At this point, I have at the second order in my Taylor expansion, because second order for this, first order for this, zero order for this, I obtain this coupling, 1/4 Qij, Hij double dot plus H00, comma Ij minus H0i, comma j minus H0j, comma I. And this is nothing but the linearized Riemann. Okay. So clearly in the TT gauge, this vanish, this vanish, this vanish, but I'm recovering the covariance of the theory. I'm recovering the full coupling to the full Riemann. So this is a small exercise that tells you that if you want to work in the TT gauge and you want to recover the full theory, well, you just guess. You in the TT gauge, in computation are much more simple because you can drop many terms. In the TT gauge, you keep only one, and then if you want to recover the original theory, well, you just complete your coupling to the object that makes sense in general relativity. No, this must be a Riemann tensor. There was questions? So to summarize, what we have done is we have expanded. You see, zero order is just the mass. You see, this term contains a zero order of H0i, but H0i is naturally order V with respect to H00, so I put it there. This term is zero order in Hij, but Hij couples to something that is naturally V squared with respect to mass, so I put it there. But there is still, so this is mass, this is dipole, this is quadrupole coupling to the Riemann. There is a little piece left, the piece in which H0ij, H0ji, the antisymmetrize. You know what it is? Let me. This is the first moment of T0i antisymmetry with a couple to the gradient of H0i antisymmetrize. Let's copy here at the bottom because that's also very important. This is, let's write it as 1/4 Hj T0i minus Hi T0j. So it was coupled to antisymmetrize a gradient of H0i, so instead of antisymmetrize this, I antisymmetrize that. It's the same thing. So the gradient of the space-time component of the metric couples to what? Do you recognize this under the integral sign? This is the first moment of T0i. This is momentum, no? T0i is momentum. I take the first moment of the momentum and I antisymmetrize. Does it tell you anything? No? It's an old friend. This, I mean, this first moment antisymmetrize of the momentum for friends is called angular momentum. Okay? So, first moment antisymmetrize of space-time component of energy momentum is a very baroque long way to call the angular momentum. Okay? So, the angular momentum naturally couples to the gradient of H0i. The linear momentum couples to H0i, and the angular momentum couples to the gradient of H0i. So, as a summary, we recover the full coupling of our composite object to gravity. We have mass coupling to H00, then we have dipole coupling to gamma I00. So, here there are two things, no? I use integration by part to stuff together the dipole and the momentum. So the dipole couples to a gradient of H00. The linear momentum couples to H0i without gradient. But then I use the trick to trade H0i for the time derivative of a first momentum of the T00, which is the dipole. So this is order 0, this is order 1 in V, and then there is the order 2, which is angular momentum. Let me call it Lij coupled to A. And then I have the quadruple coupling to R0i, 0C. And then, of course, I can go on because I have the following order, which will be Tij xk coupled to Hij, comma k. Of course, and then I have all the other orders. Tij xk xl coupled to Hij kl. Of course, at each order here, I should also consider the third order expansion of H00, the second order expansion of H0i. Here I should consider the fourth order expansion of H00, no, with 4 derivatives, the third derivative acting on H0i. But, you know, as you can guess, the exercise becomes very, very boring. But we have a shortcut. Instead of computing all of the other expansion, we forget about them, and we just say that the longitudinal components we recover because we want to rebuild the gradient of the Riemann. This will be this reconstructed the Riemann. Here we reconstruct one gradient of the Riemann, here 2 gradients of the Riemann, and so on. And we forget the longitudinal. We just focus on the TT. We could have forgot also here, but if you forgot, then we would not have done this nice exercise to see how the longitudinal pieces combine to recombine the Riemann. But we do it once, and then we forget, because then it becomes a bit undoable for the rest. Okay, so you see, you have all the couplings that come naturally in the Lagrangian formalism. So how much time do I have? Oh, I can quantize gravity in 10 minutes. So what do I have to do next? Let me check. Okay, this is a good time to pause for questions while I look for the next topic. Yes? Yes, the quadruple formula, I have to derive the v to the 10. I promised, I haven't done it. So shall I go to derive the v to the 10 then? Questions? Okay. So first we need to know what is the energy momentum tensor of the gravitational waves. Because again, we go back to our HIJTT, which is 2GQ double dot IJ divided by the distance. Sorry. Is KL lambda IJ KL. These are double dots. Okay, but now you know, no, this is just the first order expansion. Actually, there would be this here. We are already looking at something which is v squared. Now we know that there is a v0 part and v1 part. The v0 part and the v1 part do not radiate, so we forget they are not part of the T. And actually, even in the v square part, there is a part that does not radiate. It's the coupling of the angular momentum. No? Here you would get the angular momentum, the source in Hij, but it's an Hij which is not radiative. So again, it's projected out here, okay, in this TT. And as indeed the angular momentum we showed in previous slide is coupled to H0i, which is the part of the field that we kill by hand because we know it's not radiative. And then there are all the other pieces. No? There are all the other pieces that belong to this. Sorry. Working at the level of the equation of motion, what appears is this. You remember, we expanded we theoretically expanded the time dependence of Tij, and so we got a derivative of Tij, and then first moment of the Tij, then contracted with one n the direction, and then all the other pieces of the Taylor expansion. So this is the radiative piece of the gravitational perturbation. So now we have to, are we sure that this contributes to some leak of energy and angular momentum? So the standard interpretation is that how do we interpret the gravitational wave energy goes back to the Einstein equation. So we take we write the Einstein equation in this form. 8 pi g t mu nu minus 1/2 t eta mu. Okay, this is equivalent, no, to the standard. Instead of writing the Einstein tensor, which is Ricci times minus 1/2 Ricci scalar, I do the trace reverse and I keep the Ricci scalar here and I put there. And then I say, okay, now I do my Taylor expansion now in the metric. I consider background plus R mu nu first order in the perturbation plus R mu nu second order in the perturbation, and I stopped. I don't want to go beyond second order. Here I'm already at the level of the equation of motion. And then I take averages. When we take averages over, say, a portion of space which is twice or thrice, I mean, it's of the order of the wavelength of the gravitational wave I'm considering. I mean, this goes to 0 because the linear order, I mean, it's a wave. If I average over a space which is slightly larger than a wavelength, it has to go to 0. This doesn't go to 0 and this doesn't, because h square is always positive. You know? A wave is all positive and negative, but h square is always positive, so this doesn't go to 0. So what I do, and I bring this R2 on the other side, and then I say that R0 mu nu is equal average, but you know, this is the background. If I average or not is the same thing, is equal to 8 pi g t mu nu minus 1/2 t mu nu, t eta mu nu. And then I bring this on the other side. And I call this as the energy momentum tensor of my gravitational wave. This is, again, more or less the definition. Anyway, because this is second order, must be h squared. So you see, all of this, as if you like, is not really general relativity. It's just superimposing a spin 2 field to a flat background. Okay? But with all the interaction and with all the coefficients dictated by general relativity. So, so basically, you can start with the Lagrangian, superimpose a spin 2 field to a background, write down only the terms that are consistent with the general relativity invariance per diffeomorphism, and you will get to this. You get an object that is you can interpret as the energy momentum tensor of this field, because you put this field on the top of your background and you consider the fluctuation of this field as effectively contributing to an energy momentum tensor. So, yes?
Here in R2, you are only keeping the radiated.
Yes, yes. Yes, because that's very good. So in R2, I only keep the radiative part. I don't keep the longitudinal part, because the longitudinal part, they follow the source. You see, the Poisson equation has zero homogeneous solution. The only solution of the Poisson equation is the one that the source mandates. And so that energy momentum tensor is already here. Okay, if I do this, then what happens is that, okay, I skip the derivation. My computer freezes. Why? Okay, so I cannot read from the notes the exact form, but the form, I mean, it's so easy that I think I can remember. So the energy momentum tensor of the gravitational wave will be something like this. Will be d mu h alpha beta, d mu h alpha beta for the TT. In particular, remember that there are only two polarizations. So here there is a coefficient that I don't remember by heart, but I guess it's something like 32 pi g Newton. Of course, it must have 1 over g in the front, because when I want to interpret it as energy momentum tensor, it appears the 8 pi g in front that was here on the right hand side. So there must be some 8 pi g in front, then there is probably some additional 1/4, that comes from this Taylor expansion. I don't remember by heart, and my computer froze. Okay, don't trust this 32, but anyway, you find the exact number in the notes. Here, I always take the average, and when I specialize to my solution for the quadruple, just for the quadruple, I get this. So, but if I want to get the number right, I should be sure about the 32. Okay, if somebody can look at the notes, then you will tell me if the 32 is right or not. So here I specialize, and then I put T00, I take the energy density. It's radiation, so the T00 dot is basically must be the same as the divergence of T0I. It's radiation which is conserved. No, I'm losing energy density to a flux of gravitational wave. So the energy dot will be something like h dot plus square plus h dot cross square. Yeah, you remember. I have to. Sorry, no, this is not correct. Wait. I have to put in the solution. So this is the energy density. I have to integrate it. So when I integrate it, I integrate it over the omega, and I have an r square. I integrate over a surface. Yes.
I think the notes in my computer here.
Oh, thanks. Oh, thanks. So it's you have to put T00 is of the same order of T0I, and then you have basically the flux of gravitational wave also will be given. So the 32 pi joule or 64 pi g, we'll find out in a second. I went too far. It's yes, I'm fine. You have an older version. They're not in the same position. Okay. It's not the latest version. I don't remember where in the notes there. Anyway, so here what you have to put is the solution. The solution was Q, KL double dot for H, but you see here there is an additional derivative, so a Q triple dot Ij, but you, be careful. H is not Q, is Q times lambda, okay? So I need to put a lambda KL Ij. I only need to put one lambda, and in principle, each H has its own lambda. It's lambda times Q, H is lambda times Q. But then I only need to put one lambda because lambda is a projector, and you know a defining property of the projector that is equal to E square. So I only put one. And so this Q, and then there is a 1 over R square, and then there is a 4 because it was 2G square. So then it was 2GQ, and then it's 4G square, so 1G goes away with this. So the R square goes away with that. And so what we are left, I think I got the 32 right. So let me write this as, this was 1, then this was 1, this is 8. 8 pi, let me write a 4 pi here, and let me write a 2 here outside. Okay, just to recap. So the energy density of the gravitational wave, we read it from the Einstein equation, making that fundamental assumption. It's a spin-to field superimposed to a background. So we read its energy momentum tensor as this piece. There will be other pieces, but they are all 0 in the gauge we're working, because we are only focusing on the TT part. And there is this factor. Then I substitute for H the solution in terms of the quadrupole, which is the leading order solution. There will be corrections. So H is Q double dot. Here I have to look at 0, 0 components, so there is another dot. So these are triple dots. 1 over R square goes away with the integral because I have to integrate over the surface over which this T0I, the T0I is the flux of the energy which is piercing the surface at large R. So the R square goes away. I only left with the angular integration. Now I have to do the angular integration. So here there are many signs. Let me summarize. Here I get 1 over 2. If the 32 pi g was correct, I get this. Over 4 pi lambda ij kl q triple dot ij q triple dot kl. Okay? I put the quadrupole outside the integral, no? Because the integral is the integral at the surface at infinity. The quadrupole is only to do with the source. It only depends on time. It's a number with respect to the variable of integration. But lambda, no. Lambda depends on the direction, okay? Because you remember lambda was that expression of the projector. I think I should grow up in 1 minute. Yes. Lambda was, you remember, lambda ij kl is pik pjl minus 1/2 pej pkl. So is equal to delta ik minus ni nk times delta jl minus nj nl minus 1/2 delta ij minus ni nj delta kl minus nk nl. Okay, and then all of this has to be integrated over the omega divided by 4 pi. So when there is delta delta, the integral of the omega over 4 pi is 1, clearly. Now the nice thing is these integrals are trivials, because whenever I have the integral over the omega over 4 pi of ni and j, you know what this gives. So you remember, no? Lambda depend on the direction I'm looking at, of course, no? Because the quadrupole, as for instance, I'm looking at the binary, no? The binary has a quadrupole which is in the xy plane. Since the TT projection kills all the degrees of freedom that are longitudinal. So I'm looking, if I look at this, or if I look at this, I'm projecting way different things. It's like in electromagnetism, no? In electromagnetism, if you look in the direction of the dipole, for instance, you see nothing, because the electric field is only along the dipole, and if you're looking along the dipole, by definition, radiation is transverse, so you're killing. So the radiation is slightly modulated with the direction, and the modulation is here. This tells you how radiation is modulating according to where you see it. In particular, if you see from above, since all the gravitational field is moving on this plane, from above you have maximal intensity, because the projection doesn't kill anything. If you look from this way, you're killing half of the gravitational field, half of the source, because the field you're looking at must be transverse. By definition, you are imposing the lambda, the field to be transverse. And since the motion is in the plane, and you're looking from here, then you're looking this longitudinal direction. And this longitudinal direction has motion, has kinetic energy, has gravitational field that you're killing. Okay? So this lambda takes into account of this. Is the polarization projection that depends on the direction you're looking from. Okay? And this is physical. This is like an electric field. Okay, so the quadruple, the source, of course, doesn't know. This is the source, doesn't know where it has been looked from. It's the source. It doesn't know nothing about the observer. So it's out of the integral. Then we have to do this integral. So if you do this integral problem, and there is a nice simple way to do this integral, and that this object is equal to 1/3 delta ij. Yeah, that's why I put the 4 pi here at the normalization, no? Because if I contract, this is 1. If I contract, this is 1. And if I don't contract, what the integral of ni and j can give? I have nothing, it can only give the delta. And then if I do the same trick with the omega divided 4 pi, ni and j and k, this is equal to 0 clearly, because I have 3 indices. I cannot make any tensor with 3 indices. But then if I add a fourth index, and k and l, then I have delta ij, delta kl, plus 2 permutation, divided by 15. Why 15? Well, if I take all of the contraction, here I get 1. If I take all of the contraction, here I get 9. Then from one of the two permutation I get 3, from the other I get 3, 9 plus 3 plus 3, 15, and then I have to cancel this. Okay, if you plug in this formula to this integral, now I don't know, I mean, it's trivial, you just have to do. So delta delta gives 1. Delta ik, delta jl gets multiplied by 1. Then nn delta and nn delta again is 1/3, but they are 2, so I get 2/3. Delta ik, delta jl. Then I get the terms with 4 n's. I get nn nn with a +1, and then I get nn nn with a -1. So overall I get +1/30, the 3 combination of delta, plus delta ik, delta jl, plus delta il, delta jk. And then I have this other combination. I have the delta ij, delta kl. I have -1/2 delta ij, delta kl. And then I have plus 1/3 delta ij, plus 1/3 delta kl, and then so I have plus 1/3 delta ij, delta kl. I mean, if you put all the things together, then you get, I mean, trust me, you do the computation, you get 1/5 qij, you get 1/5 qij, qkl with 3 derivatives for E dot. And the contraction is delta ik, delta jl, minus delta ij, delta kl divided by 3. I mean, you put all the pieces together, then you get the result. So the 1/5 is the non-trivial thing. You get 1 power of g, because you remember we had 1/g at the denominator for this interpretation of h squared as an energy momentum tensor. Then whenever I express h in terms of h or q, I got 2 g's, so 1 g stays. The 1/5 is the result of all this subtraction, 1/3, 2/3, 1/30, and so on. This structure must be clearly there. if you have a trace, an energy momentum tensor, quadrupole tensor which has a trace, the result has to be 0. No, the gravitational wave is not produced by the trace. And indeed, you see, if one, what happened here? He moved without my consent. Why is showing this? Yes. Sorry. You see, if a quadrupole tensor is a delta j, you see here delta j here gives delta kl, delta j gives a 3, delta kl and delta kl gives 0. This is consistent. It has to be 0 because the trace doesn't source any gravitational wave. It's only the TT part of the energy momentum tensor that source gravitational wave. And that's it. Let's check the dimensions. So we have, you remember, E dot must be dimensionless. So we have Gm is a length. This is second moment, so length, cube, 3 derivatives is dimensionless. M, length, provided I add the G, this is also dimensionless, so it's okay. Let's just get the V to the 10, and then I finish. Where does the V to the 10 comes from? So here I have as a scaling, Gm over T, because one derivative, and then I have two derivatives, okay? I have mxx, again, let's get it right, just I have mxx with 3 derivatives. And then I have gmxx with 3 derivatives, and let's put the 1 over g to compensate. Okay, so this is clearly V square. This is 2. This is clearly V square. This t, let me write r and r over t. And this t, I write it r over t. So this is an additional v. This is an additional v. Gm over r is v square. Gm over r is v square. So 2, 4, 5, 7, 9, 10. This is proportional to v to the 10. If we had a theory like electromagnetism in which the previous order was radiating, you remember we had the piece that coupled the dipole, to H0i. If this was the piece that was radiating, considering that A0i would have been mxi dot. And that the energy would have been A0i dot square, then you can do the exercise of what would have been different in the final formula if the dipole was radiating and not the quadrupole. Okay? If the dipole was radiating, instead of having the quadrupole with 3 derivatives, you would have the dipole square, so 1 length less, then you can expect 1 derivative less. So you can expect that energy density, the energy radiation would have been instead of quadrupole with 3 dots, it would have been dipole with 2 dots. In an electromagnetic case. Now here we have quadrupole with 3 dots because the H was proportional and quadrupole with 2 dots, but the energy is H dot, so we get to 3 dots. For an electromagnetism, you can expect a dipole with 2 dots, and then you can do the exercise and what would be the V dependence, the V dependence of the result. But you do as an exercise. I already passed it. Thank you. Let's stop here.
Okay, so let's convene at 4:10. Maybe I will put 1 minute. And let's try to find Ricardo.
Yes, please. I think the 32 pi g was correct, but in this older version it was in some different point. Yes, it was correct, 32 pi g, yes.